Hello everyone, this is Flow Academy. Today we'll start to learn electrons in atoms. We'll cover the evolution of atom models and each of their innovations and limitations. This chapter will be finished in 3 to 4 lessons, but there are many important concepts left in this chapter, so I might not explain each of them very carefully. I'll mainly focus on the connections between them. As we all know, the number of electrons determines the chemical properties of atom because they participate in chemical reactions. It is also certain that an atom contains one nucleus in the center and electrons moving around it. However, scientists use decades to figure out how exactly they are arranged in an atom. We first come to the Rutherford model in which electrons run randomly around the nucleus. This model first brings forward the existence of nucleus, and it is composed of neutrons and protons, but it did not explain how the atom's electrons are arranged in the space around the nucleus and why they are not pulled into the positively charged nucleus. It also could not explain the different chemical properties of elements. Therefore, Bohr proposed another model. He said that electrons only move in specific circular orbits, and each electron orbit has a fixed energy called energy levels. They increase from smaller inner orbits to larger outer orbits, and they are designated by a quantum number, written as n. We must remember that Bohr introduced the quantization of energy, which means that electrons in an atom cannot exist between energy levels. Energy is absorbed when electrons move to a higher energy level, emitted when electrons go to lower energy levels. An electron can jump more than one energy level at once. For example, from higher than 1 to 1 will emit ultraviolet light. From higher than 3 to 3 is infrared light. Rutherford model did not mention this. Quantized energy level leads to the current model of electronic structure, which uses valence electrons to explain the property of elements. However, Bohr's model also has limitations. First, it only provides results of hydrogen atoms or single electron ions. It failed to fit atoms with more than one electron. Second, we can never make sure about a certain path of an electron's movement. Here, I would like to introduce the Hessenberg uncertainty principle. It says that the position and the velocity of a moving electron cannot simultaneously be measured and known exactly, because Hessenberg states that it is impossible to make any measurement on an object without disturbing the object. The third model we are going to learn today is the quantum mechanical model. We might call it QCM Model later. This model is the solution of a mathematical equation devised by Austrian physicist Erwin Schrödinger, describing the behavior of the electron in a hydrogen atom. This model determines the allowed energies an electron can have, so the notion of energy level is also applied in QCM model. It also tells the probability to find an electron in a particular location around the nucleus of an atom. First, the volume space surrounding the nucleus can be represented as a fuzzy cloud-like region called electron cloud. We can see it as a time exposure photograph of an atom. The electron may appear everywhere, and this photograph records each position where the electron emerges, but the electron is more likely to appear at some places, so the cloud is denser, where the probability of finding the electron is higher. There's no boundary to the cloud because there is a slight chance of finding the electron at a considerable distance from the nucleus. That's the brief introduction of QCM model. In today's lesson, we've learned Rutherford's model, Bohr's model, which proposes the idea of quantized energy, and Schrödinger's quantum mechanical model. We'll dig deeper into that model later. So, this is the end of today's class. Thanks for listening. See you next time.